Today we are looking at giant covalent structures, and then we'll be looking at some uses, and then followed by, this is the really important one, comparing all of the giant and simple covalent structures, including ionic bonding. And if you haven't done so already, please download this PDF so you can be making your own revision notes as we go through. So let's get started with the giant covalent structure. So we've got this word giant here again. So giant, as it is with the ionic compounds, it just means very, very big. So kind of like never ending. And we have three structures here that you need to know about. So we'll talk about each one individually. So starting off with diamond. So diamond is an allotrope of carbon. So it is carbon bonded in a certain way. So each carbon is bonded to 4 different carbon atoms, which we can sort of see. I guess this is the best example here. So we can see this carbon here is bonded to 4 different carbons. And each bond is very, very strong. So diamond has this giant network of really, really strong carbon-carbon bonds. So because diamond has a very high melting and boiling point. It also does not conduct electricity because there's no free ions or electrons to move around to carry the charge. And it's very, very strong. So that is diamond. Now let's have a look at graphite. So graphite is another allotrope of carbon. So allotrope just means a different form of the same element. So both diamond and graphite are carbon, but we've got them bonded in a different way. So graphite, hopefully we can see, is very different to diamond. So graphite is formed in layers. So we've got these layers of carbon, and the layers are made up of hexagons. So maybe not the clearest to see, but we've got these hexagons of carbon that bond in each layer. And each carbon has only bonded 3 times, which means it has 1 electron left over. So because of this, graphite conducts electricity. So it has electrons that are free to move, and because it has charge carriers that are free to move, it can conduct electricity. So graphite, is pretty much the only example of a non-metal that conducts electricity. But where are the similarities between graphite and diamond? Well, because they both have giant structures, they both have very high melting and boiling points. So graphite also has a very high melting and boiling point, just like diamond. Maybe not quite as high as diamond, but it is still pretty high. All right, so now on to our final example of the giant structures that you need to know about. We've got silicon dioxide. So silicon dioxide has the formula SiO2. And that's because the ratio between the silicon and the oxygen is 1 silicon to 2 oxygens. So what is going on? So silicon is in group 4, just below carbon. So that means it bonds 4 times. So each silicon has bonded to 4 different oxygens, and then that oxygen has then bonded to a silicon. So we can see this is very similar to the diamond. So the diamond and the silicon dioxide structures are very similar. Because they have very similar structures, again, silicon dioxide has a very high melting and boiling point. And again, just like diamond, it does not conduct electricity because, again, there's nothing to carry the charge. So there we go. So those are the 3 giant covalent structures, but we'll talk more about these later when we can compare them. And then, here we go. We've got our definition for allotrope written down for you. All right, so the next thing is, uses of graphite and diamond. So you do need to know a couple of uses. So here we have a lovely AI image. So this is an AI image of diamond being used as a cutting tool. So here we have a saw, obviously. And if you cover your saw with diamond, it makes it incredibly hard, which means it can cut through pretty much anything. So diamond is a great cutting tool, again, because it's very, very strong because of those, because of all of those carbon-carbon bonds that are very, very strong. Okay, so that's all we need to know for diamond. Then for graphite, So yeah, graphite has two uses. So let's talk about this one first. So yeah, graphite can be used as an electrode. So this is in electrochemistry and electrolysis experiments, which we'll look at in a future topic. So here are the electrodes. So yeah, so if this was connected up to a power supply, then we would have an electrolysis experiment on our hands. So it is used as electrodes because it is unreactive, and most importantly, it can conduct electricity. So there we go. It can also be used as a lubricant. So it can't be used to make a whole bicycle, but it can be used to lubricate the chain. So it is, it's a dry lubricant. So it's slightly different to oil. So oil is a liquid, which is also a lubricant. But yeah, graphite is a dry lubricant, and because it is formed in layers, that's how it works. So the layers are very easy, can very easily slide past each other. So this is why it is used as a lubricant. And then yeah, how do you think your pencil works? So when you draw a line with your pencil, you're basically just leaving layers of graphite down on the piece of paper. So there we go. So again, our uses are linked to its structure. Okay, finally, we're going to be comparing all of the structures. So all of the giant structures. And this is really important because yeah, this sort of stuff comes up a lot in your exams. So what have we got here? Well, we have a giant ionic structure, we have a giant covalent structure. So yeah, we've got sodium chloride as our example, and we have diamond, which is carbon, as our example. Here, this is another example of carbon. So this is a buckyball or a fluorine. So this is carbon, so 60 carbons all bonded together. So you might think this is a giant structure, but it's more similar to a simple structure because it ends, and because it ends, it has it has very similar properties to things like water and carbon dioxide. So if we take a look at these two, so these two are very similar, and that's because they are giant. So our two giant structures are very similar because they have very strong bonds throughout their structure. And because they've got the strong bonds, they have the very high melting and boiling point. So these are our similarities between the giant ionic compounds and the giant covalent compounds. Then with our simple covalent compounds, these are very, very different. So if we can remember back to our previous video, these are kind of like individual molecules or compounds, and even though within the structure they have very strong bonds, between the molecules they have very weak intermolecular forces. So this is why they have very low melting and boiling points. So that can all be summarized in this handy table. So we can see similarities. So we've got high melting and boiling points. So I've only put melting point, but if it's got a high melting point, it's going to have a high boiling point, and this is because of the giant structures being similar. Then, do they conduct electricity? So the covalent structures do not conduct electricity, and this is yet again because they don't have a charge carrier. So the only example that proves the rule is graphite, because it has the electrons to carry the charge. So that's how we can kind of link the covalent structures together. And then just a reminder that the ionic compounds do conduct electricity, but this is only when they are a liquid. So they can either be a liquid when they are dissolved in water and you've got an aqueous solution, or when you have a molten solution. So when you provide lots and lots of heat, break all of those strong electrostatic attractions between the ions, and you end up with your molten salt, then it conducts electricity. Okay, so definitely remember this table and figure out how to apply it, because this will definitely come up in your exams. Okay, so that's all from me. So thank you for watching, and I will catch you in the next one. Ciao.